In this third class of Chapter 7 of the course of Basic Geometry, the following topics are presented: construction of hyperbola, tangent to a point of hyperbola, auxiliary circle of hyperbola, director circles of hyperbola, asymptotes of hyperbola, other definitions for hyperbola. In this first slide of this third class of Chapter 7 of this course of Basic Geometry is presented Figure 7.8, which presents the method of construction of the hyperbolic curve. For the construction of the two branches of the curve of the hyperbola, it is drawn the transverse axis with the points F1, F2, A1 and A2, and then mark the point P. With center in the point F2 is drawn a circumference with radius A2P. With the same radius, we center at the point F1 draws another circumference. Next, I draw two circumferences with radius A1P and centers F1 and F2. The intersections of the circles drawn with centers in F1 and F2 generate the points M1, M2, M3, and M4. The procedure is repeated for other points Q, R, and S. With the generated set of points, it is possible to draw the two branches of the hyperbola. In this second slide of the third class of Chapter 7 of this course of Basic Geometry, the figure 7.8 is again presented, which shows the method of construction of the hyperbolic curve. As the difference in height dimension of the drawn circle has the dimension of the constant of definition of hyperbola, the points M1, M2, M3, and M4 satisfy the rule that the difference in the dimension between the two vector ranges must have the value of the constant of definition of the hyperbola. The same is true for point A1 that belongs to the curve. The difference between the line segments A1, F1 and A1, F2 has exactly the dimension of the segment A1, A2, which is the constant of definition of the hyperbola. Because segment A1, F1 has the same dimension of the segment A2, F2. In this third slide of this third class of Chapter 7 of the course of Basic Geometry, you have the definition of a tangent at the point M1 of the hyperbola curve. In Figure 7.9, a point M1 is marked on one of the branches of the hyperbola curve, and the two vector rays connecting the point M1 to the focal center F1 and F2 are then plotted. In this way, the angle F1, M1, F2 is formed. The bisector of this angle is then drawn. The bisector of the angle is the tangent to the curve at the point M1. This curve is the branch that has the focal center F2. In this fourth slide of this third class of Chapter 7 of the course of Basic Geometry is presented definition of the auxiliary circle of hyperbola. Figure 7.10 shows the auxiliary circle of hyperbola. The auxiliary circle of hyperbola has center O, which is the center of the hyperbola, and radius equal to the half the constant of definition of hyperbola curve. The auxiliary circle of hyperbola is unique. This fifth slide of this third class of Chapter 7 of the course of Basic Geometry presents the definition of the director circles of hyperbola. Director circles of hyperbola are presented in Figure 7.11. The director circle of hyperbola are the two circles centered on the focal points of the hyperbola with the radius equal to the constant of definition of the hyperbola. Then the hyperbola has two director circles, one for each branch. This sixth slide shows the properties of the asymptotes of hyperbola. The figure 7.12 shows the two branches of the hyperbola curve and its asymptotes A1 and A2. The two line segments A1 and A2 that tend to infinity are the asymptotes of the hyperbolic curve. The points of tangents of the two segments with the two branches of hyperbola are also at the infinite. The axes of the hyperbola are the bisector of the angles formed by the two asymptotes A1 and A2. The two asymptotes are symmetrical in relation to the axis of the hyperbola and pass through its center O. In this seventh slide, continue showing the properties of the asymptotes of the two branches of the hyperbola curve. The figure 7.12 is displayed again. For the construction of the asymptotes of the hyperbola, a circle is drawn with center in the center of the hyperbola O and with a radius equal to the half of the distance between the focal points of the hyperbola. Next, two segments of a line perpendicular to the transverse axis are drawn passing by points A1 and A2. At the points of intersection between the circumference and the two perpendicular line segments, the points M, N, P, and Q are marked. Using the points P, N, and Pn line segment is drawn, and using the points M and Q points another line segment is drawn. These two line segments are the two asymptotes of the hyperbola. The two asymptotes pass through the central point of the hyperbola. In this 8th slide, the properties of the asymptotes of the hyperbola branches continue to be shown. The figure 7.12 is displayed again. The 4 points M, N, P, and Q form a rectangle. If the line segment K constructed between points A2 and Q has the same dimension of the half of the constant of definition of the hyperbola is equilateral, and the rectangle has the form of a square. In this case, the asymptotes are perpendicular. This last slide of this third class of Chapter 7 of the course of Basic Geometry presents some additional definition for the hyperbola curve. The figure 7.12 is displayed again. The first definition says that the hyperbola is a convex curve because any line segment does not intersect the hyperbola curve in more than 2 points. Any point x of the plane lies within the curve, belongs to the curve, or is outside the curve according to the value of the difference of the distance to the foci is greater, equal, or less than the constant of the definition of the hyperbola curve.